What's going on, everyone? Today's video is going to be pertaining to electron configurations and how you write electron configurations. But before we get into discussing what an electron configuration is, there's a couple rules that we have to learn. And the first one is dealing with the Aufbau's principle. Aufbau's principle states that as the protons are added into a nucleus, the elements are going to also have to add in electrons in a similar fashion, so that way they counterbalance themselves. So as you add a +1 charge to the nucleus, you have to add a -1 charge into the electron cloud. And so that's a normal fashion that we observe on the periodic table. The second rule is Hund's rule, which states that each orbital has to have one electron in place before you start to put a second electron in. And that's based off the fact that for every orbital, you can have 2 electrons. And so that deals with quantum numbers, and specifically the fourth quantum number, m's of s. So m's of s is going to be plus or minus 1/2. And we're going to see how this is shown in the diagrams that you observe over the next 2 slides. But for right now, in the purpose of Hund's rule, we need to understand that there are 2 electrons per orbital. And when we look at this diagram that you see here, the box that you see, each box represents 1 orbital. Now the whole entire thing represents the D shell. In this specific case, it's the 3D shell. So if we were to fill electrons into the 3D shell, what we would do is we would start off with, let's say we had 6 electrons, and we want to fill in 6 electrons for the 3D shell. What we would do is we would do 1, 2, 3, 4, 5, and 6. So what we see here, this is plus 1/2, and each of these are plus 1/2. And then when you get back to the other side, now this is minus 1/2. So the reasoning for it being plus and minus 1/2 is because it's a magnetic field that's made because of the spinning of the electrons. So as the electrons spin this direction, what happens is it generates a north pole and a south pole. And so that's where we get our arrow that goes up. If we spin in the opposite direction, well, that's going to create a north pole that's opposite from the other spin, and that's where you get the minus 1/2. And so the electron spin is important, and it follows with Hund's rule, and we can see this as we go throughout this diagram. So moving to the next slide, we're going to talk about how we write an electron configuration, how we utilize this diagram in aiding us to write an electron configuration. Ultimately, we're going to get to the point where we can use the periodic table and we don't have to use this diagram. But for right now, for our learning purposes, we want to start with this. So let's start off with the most basic element. Let's start off with hydrogen. Hydrogen has 1 electron. And so you say, well, where can I start filling this in? Well, you start from the bottom and you work your way up. So when we look at hydrogen, hydrogen's got 1 electron, so we're just going to go to the first orbital at the very bottom. We're going to draw our arrow in. And so the configuration for this would be 1s because it's found in the 1s orbital. And it is also, it has only 1 electron there, so we give it an exponent of 1. So this is the designation for the electrons found, and this number represents the number of electrons that are found in that specific shell. So if we go to, let's say, carbon. Carbon's got 6 electrons, and we want to fill this in. Well, we start at the bottom just like we do with hydrogen. We've got 1, 2, 3, 4, 5, and 6. Notice we used Hund's rule with 2p. So when we want to write the configuration, we're going to have 1s2, 2s2, 2p2 because there's 2 electrons in each one of those shells. And so the configuration would be what we have wrote here. So it's sort of a coordinate diagram. It helps us to identify where the atom's found and the number of electrons that are there. If you add the exponents here, 2 plus 2 plus 2, that's going to equal 6 electrons. So these exponents, when you add them together, they should end up being the same number of electrons that you find on the periodic table. There are a couple exceptions, but for right now, we're just going to keep it simple and do a neutral atom. So let's do chlorine. All right, chlorine has 17 electrons. And you're going to notice that we already have several in place here. So we've got 6. So we're going to continue this. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So the configuration that we would write out would be 1s2, 2s2, 2p6, 3s2, 3p5. And if you add up 2 plus 2 plus 6, 10 plus 2 plus 5 is 17. So that matches with what we're supposed to have. And we observe that we have used Hund's rule as well as we travel and track the electrons through each energy shell. So where it gets tricky is after you get through the third row on the periodic table. So if we do scandium, scandium has 21 electrons, and it's the first transition metal that we come to on the periodic table. So we're going to fill in the periodic table. So now we're at 20. So you can't go to 4p because it's higher. But what we see here, if we go straight across, you have your D block. And scandium is found in your D block. And there's only one electron left here, and that makes 21. Now, once we fill in all of your D blocks, then you can go to 4p, then 5s, 4d, 5p. Now, this chart that you see here is incomplete. It does not have the f orbitals, and it doesn't go all the way up to the 7th row on the periodic table. So you got to be careful of that. Now, as far as scandium is concerned, let's figure out the configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. Your transition metals are always going to be one less than the s shell. So in this case, we had 4s. It goes to 3d. If we have 5s, it's going to go to 4d. If we have 6s, it's going to go to 5d. So that pattern stays consistent as you look at the periodic table. So I'm going to switch to the next slide. So as we look at this periodic table here, what we observe here is we see that the S shell is found on the left side and the P shell is found on the right side. Then you look at the D shell that's found in the middle. So for scandium, we just looked at scandium. Scandium stopped at 3d1 because we went through 4s2, then we went to 3d1. And so if we went to zinc, it would be 4s2, 3d10. So all we're doing is adding up to equal the number of electrons, and we're matching that to how the placement of the element on the periodic table. So for the S shell, if you notice, there's only, if we look at this, there can only be 2 electrons found in the S shell. For the D shell, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this, the max that you're going to have in the D shell are 10 electrons. In the P shell, you're going to have 1, 2, 3, 4, 5, 6. There are 6. And then finally, your F is going to be 14 as we count across. Now notice that your F group, if you look right here, your F group travels down. And so your F group really fits in between the first and the second element in the D block. But we don't see the F block until we get down to rows 6 and 7. So we don't really have to deal with them too much unless we're focused on those lower elements on the periodic table. So now remember that your S block, your S orbital, there's only one orbital. For your D, there was 5. And this goes back to that previous slide. For your P, there were 3. And then for your F, there's going to be 7. Because remember that there are two electrons per orbital. And so that pattern is going to stay true for all your electron configurations that you're going to write out. So let's do a couple examples here, and I'm going to do some erasing of this slide. Too much going on here now. So we are going to look at sulfur. So sulfur, you always start from the top and work your way down on the periodic table. If you were to use that table that we on the previous slide, well, we would start at the bottom and work your way up. But like I said, you don't have to have that table. You could use the periodic table. Just notice where sulfur is. Sulfur is going to start with 1s2 because you got to go from top down. Then we're going to go through 2s, and that's 2s2. Then we're going to go through 2p, and there's going to be 6 in that group. So 1, 2, 3, 4, 5, 6. Then we go to 3s2, and then we go to 3p. Now we stop sulfur here, and 3p would be 1, 2, 3, 4. So the configuration for sulfur would be as you see drawn here. If we did, let's say, bromine. Bromine is found right here. So let's do bromine. So bromine, you would start again at 1s2. You go to 2s2. Then we go through 2p6, 3s2, and you continue this all the way down until you get to bromine. And then we go to 4s2. All right, so now we're here. Then we see that we're getting into the D block. So now it's going to be 3d10. And then we go through into 4p. So your S and your P's are always the same value. The two that change are your D and your F blocks. So let's finish this off. So 4p, 5. So this will be the configuration for bromine. As you can see, as we go further down the periodic table, these configurations start to get longer and longer and longer. There's one more element I want to do here, and that is lead. All right, so lead, we start again at 1s2, 2s2, 2p6, 3s2, 3p6, just tracking it down until we get down to row 6 here. 4s2, 3d10, 4p6, 5s2, 4d10. So here we are. We're tracking through this. So we're going through 5p6 now. Now we get down to the 6th row. So 6s2, we get to 5d. Notice that 5d then tracks down to 4f. So we have both 5d and 4f. Now the nice thing about this is lead is on the other side of those two. So we have 5d10 and 4f14. So you have to count all of your d's and you have to count all of your f's. And there's 14 in the f and there's 10 in the d block. Now we are going to finish with 6p2. And that is configuration for lead. As you can see, all you're doing in the configurations is you're tracking from top down, and you're just keeping count of your S, your D, and your P electrons. If there are F electrons, you have to make sure you include them as well. But notice that those only occur in rows 6 and 7. Okay, on the previous slide, we talked about how to write electron configurations. On this slide, what we're going to do is we're going to talk about how we go about writing electron configurations using the noble gas configuration. And as we saw with the example of lead was very long because it basically goes from the top almost all the way down to the bottom of the periodic table. So if we use lead as our example here, what we do is we draw brackets, and in the brackets represents the noble gas that lead is most like. The way we figure that out is that we go up and to the right. This is the noble gas that is most like lead. It cannot be radon because it doesn't have enough electrons to be radon, but it could be xenon because it has the right number of electrons. So in the brackets we would write xenon. Now what that does is it covers all of the electrons that I've shaded in here. So when we write the configuration, the noble gas configuration for lead using the noble gas configuration, we will start with xenon, and then we will start on row 6 that lead's found on. So we would have 6s2, 5d10, 4f14, 6p2. So that would be the configuration for lead. And so you see that this configuration is a lot shorter than the previous one, which the previous one is called the complete electron configuration, and this is called the noble gas configuration. If we look at another element, so let's say we look at aluminum, all right? So aluminum would have a noble gas configuration of up and to the right for the noble gas, neon. Then we would start at row 3, that'd be 3s2, 3p1. That would be the configuration for aluminum. Now, if we look at cobalt, cobalt would be up and to the right. So it's argon for the noble gas. We start on the 4th period, so that'd be 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. So it'd be 3d7 for cobalt. If you look, there's a pattern. Every time I talk about the noble gas configuration, I always go up and to the right, and that would be the noble gas you put in parentheses or brackets here. And then you start on the row that the element's found on, and that's how you get the noble gas configuration. Now the good thing about the noble gas configuration is that you can figure out the valence electrons of the elements based off of the last S and P. But the S and P must have the same energy number. So if we look at aluminum and we ask, let's say, what are the valence electrons for aluminum? Before I answer that question, we got to make sure we understand what a valence electron is. So the valence electron are the electrons that are found in the outer shell of the electron cloud. So all the valence electrons are found on the outside. So when we look at aluminum, it has 3s2 and 3p1. That is the last S and P. They have the same energy value, so the exponents add up to be 3. So aluminum would have 3 valence electrons. If we look at cobalt, cobalt has 4s2, 3d7. There are no p electrons based off this noble gas configuration. There are, but they're not counted. The only ones we count are the last S electrons we have here, and there are 2 of those. So for cobalt, there are 2 valence electrons. As we look at strontium, we see that there's only 2 less electrons, so it's 2. As we go through and we look at the different elements in the periodic table, and we figure out the number of valence electrons, we can use the noble gas configuration to help with figuring that out much faster. Now, another way that you can do this is, and this is shown here on this slide, is that the number of electrons can also be the same as the group number that you find on the periodic table. So if we look at hydrogen, for example, hydrogen is in group 1A here. So group 1A has 1 valence electron. If we go to 2A, it's 2 valence electrons. All of the transition metals have 2 valence electrons because this is your D block. And D electrons are not counted. Then you get to the P block. 3A has 3, 4A has 4, 5A, 6A, 7A, and then 8A. So if I asked you how many valence electrons oxygen had, you could write the configuration. But if you understand the way we count the group numbers, then you would know that oxygen has 6 valence electrons. So you can do this for anything. Calcium, how many valence electrons does it have? It's in group 2A, 2 valence electrons. Indium is in group 3A. It has 3 valence electrons. Xenon is in group 8A. It has 8 electrons, valence electrons specifically. Selenium is in group 6A. It has 6 valence electrons. So as we count the valence electrons, what we have to pay attention to are the group numbers. Or you can use the configurations that we were talking about in the previous slides. Either way, both ways work, just depending on which way you understand better. But remember that the S electrons and the P electrons are the only electrons that will count as your valence electrons. The D electrons do not count, and the F electrons do not count because they are lower in energy in comparison to the S and the P electrons. So, just some practice problems for you to work on. Alright, so you can look at the elements on the periodic table, and you can work on writing both the complete and the noble gas configuration. And as you're doing this, go ahead and work on figuring out the valence electrons as well. It's good practice. The more practice you do with this, the better you get at it. It's just like anything, you got to practice to make it perfect. Thanks guys for watching. Leave a comment if you have any questions.